So you are in a grid world and you can be rotated. That means I could, for example, start in this state. I'm like, oh, I'm in the center.
Oh, left and right is rotation.
Yes. I'm in the center and now,
Yeah.
oh, I can rotate to the right.
But then as a human, I can immediately see then we can express this as saying you have a rotation and a position in the world, and then
You don't care about
forward
that.
maps.
You don't care about that right now. About how do we represent the world. In fact, this is about that I would like to understand what is the structure of the world without knowing how to represent the world, what anything means in the state. So we get something like this, right? That's the thing I can do. Can look up and then I can rotate left, can rotate right. Right? Makes sense?
Mm-hmm.
The world state graph is the graph where we have the vertex is the state of the world. Edges are possible transitions between the world states. So now this is not complete. There's another thing like this over here, right? Which is sort of, in some sense, the same. That I have all of these arrows. If I'm just gonna have bidirectional arrows, I'm just gonna draw them as this. And now we have these arrows where I can like move like this when I do like left and right. I can do that. And if I'm here and then I do the forward action, I would move over here, right?
I guess as a general result, I agree that
And from here, if I do forward, I
understanding
would
the
go
world
here.
probably means figuring out the symmetries that are present in the world as a first step. And you're basically saying, okay, we have this rotational symmetry, which we can first discover, and then we can use it to...
I don't understand what you're talking about at all. I don't know what you mean with symmetry. Maybe I will just explain further. I'm not saying anything right now about how we do anything with this thing. I'm just writing down what is this graph. So maybe you mean the right thing. Though so far I didn't say anything about that, right? I'm literally just writing down the world state graph of this environment.
Well, what is the forward?
Well, so forward would move you in the direction that you're pointing. So here, you would go over to this point.
Yeah, and then, well, what's the other arrow?
Which other arrow? This one. Well, if you think about what is this state, I thought it's, well, I left it implicit. If I write it down explicitly, then this would be, I am facing down from this position. So moving forward would move me to this again. And here it is like I'm in the top spot, but pointing to the left.
Okay.
And so we get this thing, and we get, so like I'm now gonna omit it. Does this make sense when I omit this?
Yeah.
Like here's this thing, we got another of these things over here. We get one over here. We have one over here. We have one here. We have one here. Does this make sense?
Yeah.
And then they are connected. It's always that if we are like, we sort of always go like to the end piece of the node. Actually, we also have one here. Does this make sense that we go to this end piece? It's like from here, we go over here. From here, we go over here. It's like we retain the
Yes.
position.
Yes.
Okay, so this is the world state graph. I didn't draw it completely, but now it should make sense. What's the structure? Is this a lattice graph?
Yeah.
No. How is this a lattice graph? This is definitely not a lattice graph.
It's a lattice where you have, in each point, you have this 4-node diamond graph embedded.
Yes. That's correct. That's the inference I want to make. But right now, this is not a lattice graph. Like this vertical graph is not a lattice graph.
What's formally a lattice graph?
Well, I don't know how to write down the formulae, but intuitively, it's like a regular grid. Well, if you draw a bunch of, imagine you draw a bunch of hypercubes in dimensions n, and then at all of the edges you place vertices. So for example, like this. If I have two hypercubes, which are rectangles, I could say like, yes, look, I make this like grid. And so like now I place vertices at these points.
This is actually what the lattice graph is.
Yes, it is.
Like, can't you also have
Yeah, you can also have like triangular lattice graphs. It's like some specific kind of lattice graph. But
yeah,
now
and I
it's then
think
even less
you
clear
can
what's
also
a
have
lattice.
diamonds.
I don't think so. So in some sense you're right, because
supposed
for
to be
example
a
for
gotcha or
R2,
what?
no, for R2, no, I'm saying you're right. I'm saying there are more ways to do this. It could be like this, which is like rectangles, but it could also have hexagons, for R2 at least. And then like a hexagon. Like this could also tile R2. Higher dimensions, I'm not sure, also triangles would tile it. So you could like have like this graph, basically just a grid. We have like this, or maybe the other direction. It would also be considered a lattice of the in graph theory. But any regular tiling. So if there's some regular tiling in higher dimensions, where you have like some polyhedra, for example. Polyhedra? Yeah, one polyhedron. It's maybe singular. You have a polyhedron that also tiles it, the R3, then it would work. And if you have like an n polytope that tiles n-dimensional space, well, then it would also be regular tiling, where you place like all of these polytopes, and then you have the edges of the polytopes be like the edges in the graph, and the vertices be the vertices. The graph. So yes, this could be more. In this case, it is a rectangular or two hypercube lattice graph. So this is a particular. So this is not a two hypercube lattice graph right now.
Yeah, and you can like find some structure in it still. And now
So
you
yes,
say,
what do you mean with structure here?
well, it's a lattice of not of points of world states, but it's a lattice of groups of world states. And by group, I don't even mean only like a set of word states. I mean like an actual group where you have, which is a rotational group.
Yes, I haven't quite understood that still, what you mean with that. Do you mean like this lattice here would be a group, for example?
I mean, it is not a, like, you can have a group which represents, or like there are symmetries in that, right? Like this lattice is symmetric. I mean, if it was infinite, or if you wrap it around, then it's symmetric if you shift it one to the right, and symmetric if you shift one to the top.
Ah, that's what you mean. Ah, okay, now I understand what you mean with symmetry. Yes, actually, the kind of structure, detection and extraction I'm thinking about is more general than. Well, I guess you can think about this symmetry, but for example, what you call this symmetric? Okay, I guess here, one example that's easy would be like this. Here's a tree. Is the tree symmetric? Another example would be, what about this?
Yeah, the tree is the free left-right group. That's commutative. No, not commutative.
What about this? Is this symmetric? I think there is something symmetric about this. If you think about it in terms of, look, I can look at this thing, and then at this thing, and then at this thing, and then at this thing, and think about, how do I get from here to here? How do I get from here to here? How do I get from here to here? Like what's happening? Like maybe we call this like f. Maybe there is sort of a function f, where f has a type, taken a graph, and return a graph. And here the function might be something like add a vertex. So like implementation might be something like we take in the graph, and then we're like extend left, extend right, G. Extend, I mean like, yeah, look at this graph and now like go to the left, go to like this line here, place like vertice always to the right, and then like go find the bottom thing, add the vertex there. This would be like, this like describes like, I mean, this could go on, right? I could apply this again to this. This describes sort of like the symmetry is that this rule that determines how does the graph, if I go further to the right, what kind of graph is there? This rule doesn't change. There is sort of a way, a rule, and I guess there's probably a bit of stuff missing, but there is sort of a rule that can tell me if I'm at some point I can think about selecting some structure at the point. Like notice that, like, oh look, like right, like I could notice that I'm in this 4 block here, because like I notice here's another thing and here's one missing. So like this is how. This is where this is one sort of segment, and then it's like here again I could detect this sort of segment because like I can notice that here we add something and here we can't go to the left anymore. And then I can say like I'm in this segment. I could detect this by like going down and looking for this kind of structure here, but I can't go to the left anymore.
The thing is,
and now,
in general, a function like this always exists, right? So what you mean it's like a nice function?
Yes, it might be uncomputable. Probably we don't care about that case. But yes, definitely the functions might be nicer. Like in this case, it's very nice, right? Like this seems like really easy. Like I could discover this pattern, and now I describe a graph that might be infinitely large with this, right?
Yeah.
And it's not a lattice. Or like this is actually now we can turn it into a lattice, right? Because these nodes, we could think about it like this. We have these different sort of other graphs, and what they are is we know that based on the f that we're currently in. So this would help us compress this a lot, especially if we had the inverse of f, and then we could go back. Then we only need to store the current graph, and we can still sort of like predict any graph. Probably we can also analytically compute. Like it seems like probably if you do something like, wait, is this how you would say this? I think maybe not. How do you say I'm applying f a bunch of times? I think it would be like compose, right? Compose NF.
Yeah, so that. No.
That's what GPT
definitely not like this, but probably you would write repeat in this.
Repeat?
Compose MF is composing M with F, which is not what you mean.
No, it's not, because this compose is not this. This is the binary operation. This is the repeat this. Yes, I could write this. Repeat N F fold left this, and that would work. Okay. Then compose f and f. You cannot compose a natural number with f. If you would know the type of n, then it would at minimum be clear, right? And it's like, yes, I know what this is.
Yeah.
So I could write compose n. Okay, now we have an arbitrary function. Takes one argument. So I guess we would say.
You need the dependent types.
No. We just need system F type theory.
Oh no, sorry. I mean, if you want to. So I thought about how you in Lean you can use compose for both. Could have a dynamic type for the first thing, which is the union of natural numbers and function. And then you can, in the code, write if it's a natural number, then do this, otherwise do this.
Yeah, that would work. Nice. Yeah, but this is
bad.
Is why?
If you actually do that.
Really?
I mean, because the name is like compose always it's just composition with two functions. I mean, for that, yeah, I mean, you could do that, but it's like, I feel like it's bad to
I think
overload
compose is this. Or we could call it autocompose or endocompose.
it. Okay. Yeah.
Okay, and that is we could infer this kind of structure, and we could say like, oh look, this is the structure. It's very very good.
Yeah, I think it's actually hard to do it, but yes, in principle you can.
Yeah. I'm not right now saying yes. Okay, I guess this is important, but like the idea is this is possible. Well, here's possible, right? I mean, and in tree, you can notice that you're in a tree, and then you're like, I don't need to store the entire tree. I can actually like not store the entire tree, and I can also know if I do 1 million times left, what's the state I'm in, or sort of like. That is a thing that we want to get to, which I didn't talk about how to do yet. But if you sort of have the state also on here, and you know how the state changes with an action, and that is sort of like also determined, possible to be determined by a function. Like we could go one step further, right? And we could say this function also takes an action. Or like, okay, now I'm confused about this. But basically, I'm saying something like, well, or like, let's think about a simple case, which is the action always has the same effect. If I do, for example, in this thing here, in the example from before, if I go forward, it always, well, okay, actually it's a bad example. Because forward actually depends on the current state, what it does. So actually, yes, this is it's so the very simplest thing, if you abstract this into just a 2 hypercube lattice graph, then we can notice that when we're moving around, we're always having the same effect on the environment. Always, if I move to the right, I always increase my x position by 1 or something like that. It's sort of the same delta applied. Like if I take one step forward, like then do it again, it's sort of in some sense the same thing happens, which I don't know how to say formally yet. But this intuitively makes sense.
I think for me, like even that we as humans, like I look at your graph and I see the structure immediately, right? Like and you basically, even if we ignore the actions for now, if you just look at the graph, you want a world model which like explores part of the world, or like an algorithm, you explore part of the world, and you deduce like how the world is from like this limited sample. Yes. It's like Occam's razor or whatever. And I'm so fascinated right now that like as a human, I can look at your graph and I immediately see the rule you used to produce it. And I know how to continue it further.
So, yes. So that should be evidence that you can do this.
Yeah, and you will now want to have an algorithm which like does this.
For this is easy, right? For this specific. Actually, what I wanted to talk about,
yeah, you
which
can
I didn't talk about.
Any particular thing, any particular exact setting, you can code.
The math formalism I wanted to tell you about, but I need to actually leave very soon now, which I didn't talk about at all, is how I formalized this kind of structure in general. Because...
Okay, yeah, tell me fast. I can understand math fast, I think.
Okay, basically we have a function that is like the kind of graph that can be abstracted. This function takes in an edge regular lattice graph
And this
And
is
it
your
works in
like normal lattice.
Yes, some lattice.
Okay.
Some lattice we know how to handle. Could also be like a hexagonal lattice or something. The only important thing is, but the idea is, yeah, this is some graph we know how to handle. Actually, okay, now I notice it's actually much more general than I thought again. Because this could be any graph, really. Any graph that is nice. Then we take another graph. Then we take in a function that maps a vertex to an edge, I guess. Well, it doesn't really matter. And then we return a graph. This is the function which like does the reverse of the abstraction, where we're like, look, I have this graph. Now I have two graphs. I have this one graph, which is nice to handle. So I'm like, oh, if I had this graph, would be good because I have some algorithm maybe that works on it. And then I have another graph, which can be any graph. And then I'm like, yes, replace all the vertices in this nice graph with this graph, and I'll get something different. Like that's a way to which I can generate this graph with it. But also lots of other graphs. Like the general thing that can be abstracted, like if there are like 10 vertices.
I don't know why don't you just have graph, vertex to edge to graph? Well, what's the first thing about? Well,
first of all, this is a function because you need to reconnect the vertices.
yeah. I mean, you have this function, vertex to edge. You have a graph, which you convert, and then you get out a graph. Why do you have two graphs?
I mean,
In the beginning.
the graph here is the one that we place in the vertex. This is the graph that is placed at every vertex.
But then you don't need vertex to edge, right?
No, because you need to know how this graph, like now we placed it in here. Like here we have this big vertex. And I would like to place now this like smaller graph in here. So this big vertex has like these two arrows in. And I want to place this in there, but I need to know how do I map this F thing in here? And how do I map sort of, I guess, this F thing out here? To what vertex does it connect?
But then don't you need vertex and edge to edge? Yeah, anyway,
I mean,
there are some details. Maybe you need
changes,
changes,
in the
maybe
small
not.
graph, yes, probably. In the vertex, that you need to say like, what edge needs to be mapped to this? You use this function, and then in the implementation of the function, you are like, for each of the vertices of this graph, you run this function telling you how to connect things.
Yeah, okay. This is such a function. Okay, this is fine.
Well, that's a way to make this more general with math. Now it is really general. Now it doesn't work just for this specific example. Like it would also work for examples where maybe you as a human would not find it obvious. And this could be generalized further by doing like this thing where we have the function. Okay, that's basically it.
The formalism now, but now what you actually want to do is you want to observe actions or parts of the graph, right? And you want to abstract this function. You want to construct the most plausible generator function for the observed graph, right? And then this is the actual algorithm. So now you have put a formalism on it.
No. Wait. So like, or like maybe yes, that's also a thing to do. The thing that you would do with this is, if I can check whether a graph you give me some graph, and I can check can generate a graph. If that's the case, I know some algorithm that works sort of to abstract this, but this is constructing a graph. I can have a separate algorithm that is like, yes, given that a graph was constructed by this function, it can be abstracted in a particular way. A certain kind of abstraction algorithm works on it. And now I can be checking if you give me a random graph, does is able to generate this graph? Yes, I can just use this other algorithm. That's the idea. Well, part of it. A bunch of other nice properties. So So like it's not about this. So like this is about detecting whether a certain hard-coded sort of structure is there, and whether if I have an algorithm that can do stuff, if I get something of this hard-coded type of thing, then you know you can use that algorithm now.
Yeah. Okay. So if this, maybe I want to comment on a general note. So the first question is, do you think these kind of things are like info or exfo hazards or whatever?
Why?
And if not, I think for you to get this out there as soon as you have some like nice thing which is progress but not dangerous if people don't know how to apply it or something, then you could try to publish something. And if you have published something, your chance of funding are like times
Yeah, I
lots.
don't even need to publish it. I could just, or like maybe I do. I don't know.
I mean, you can also publish on Less-Wrong, but publishing as a paper somewhere would be a lot more prestigious. But whatever. I mean, maybe not for, maybe for Less-Wrong it's enough for Less-Wrong funding. Basically, you can publish on Less-Wrong.
I
So that you
totally
have a
agree.
goal to work. Yeah, so then you can work towards such a goal.
Yes.
Which should be some motivation additionally too.
No, I don't think it works like that. I think I want to do this because it seems now good to do this such that I increase my understanding of what I'm doing. I can't do something because I think now I get more funding or something, because that's ridiculous.
No.
Well, but now I notice that it's useful, because this seems useful to me, and I didn't notice it if I hadn't the math formulism. So apparently math formalisms is good, and therefore, well, I won't want to use it more. Which also then is good for other reasons that I care less about than that math makes me better at thinking.